The QR code is cut off. Can you probably go to menti.com and then use 3903-6402. How about this? Does it work? Shape, their name, ID. What defines a human, vehicle, and building? What differentiates between human, vehicle, or a building? So we can say a human would have eyes, nose, which we don't find in vehicle. Whereas in vehicle, we find lights, we find wheels. And a building, it has windows, which is quite similar to what a vehicle would have. Correct? Shape, their name, ID. Okay, so today's lecture is gonna be a bit long, so let's get started. Had your dinner? Yes, I had my dinner. Body? Yes, body. So a human would have a body with flesh. A car would have a steel body. A house would have a concrete body, right? And they are different by texture, correct? They can be different by color. Yes, they can be different by colors. So now, these are all the features that we are trying to define for a human, a vehicle, or a building. But all of these answers tells us that no, we are not there as a computer scientist to teach a computer how to see. Okay, so today's topic is going to be feature extraction and image classification. It's so far one of my favorite lecture to deliver. So just a recap of what have we talked about so far. We have talked about image representation, where we mentioned there are three types of ways to represent image. We have the binary way of representing pixels with 1 and 0. We have grayscale, and we also have RGB. Yeah, and last week we talked about image operations, and we talked about data augmentation, where we can use a certain function to change the orientation of a particular image or object to make it have multiple representations of an item. So then we can then subject these disoriented images to teach the computer and say, hey, when you see this item A in this orientation, it belongs to A, and when you see another orientation of A, it is still an A. So this is what have we talked about so far. So we are so close to our objective, right, where we started this computer vision with, which is image classification, the very core computer vision task which we want to learn during this class. So now, what is still missing? What is the one missing step before we can do image classification? So now we have known the image representation. We are able to now change the JPEG file or PNG file into an array of numbers. And we are also able to operate on these numbers, operate on these digital images. So now the next step is, before we can classify these images, we want to talk about a topic called feature extraction. So now, as we learn machine learning machine learning using structured data, what have we seen so far are the features which are organized in structured tables. So we have all the features which are predefined on a certain observations. But images, so how can we then define the features for these images? So in today's lecture, we are going to talk about image feature extraction. So we are going to talk about what are features, what are some of the traditional feature detection techniques, what are some of the modern feature extraction techniques. So those are deep learning related. And whenever we talk about deep learning related feature extraction techniques, we can't run away from talking about this CNN, convolution neural network. So then we will also talk about the core task that you want to learn in this course, which is image classification using CNNs. So we'll talk about this, how do we use this convolution layer to learn the features from a particular image. We'll learn how to use this ReLU layer to introduce nonlinearity, and also pooling layer to reduce data size, as well at the same time preserve the spatial invariance. So the first topic that we are going to talk about is image feature extraction. So before we start to talk about this feature extraction, just to give everyone the same context on the data structure of images. So images, we have talked about it many times, that they are unstructured data. The reason why we consider them as unstructured data is because they do not have a predefined columns, or they do not have rows to represent features. So far, what have you seen on a particular image are just boxes which are represented by numbers. So these are pixels. So then, how do we represent image? So in a normal structured data set, what we have is all the features which are organized in a table format that comes along with its label. So we are trying to use machine learning algorithm to learn these features and to predict a particular label. So this is a common task. But what if we have an image that consists of multiple boxes? So now, what are the images? This is what a computer would see, an array of numbers, a 2D array of numbers. And how do we then enable this computer to say that, oh, hey, this is actually 80% Lincoln, 10% it would be Washington, 5% would be Jefferson, 5% would be Obama. So how do we enable this to happen? Yeah. So this is feature. So how do we craft a feature from this unstructured data is the topic that we are going to talk about today. So what are features? So early in this lecture, I asked everyone what is a feature. So what is a feature that would represent a human? What is a feature that would represent a car? And what is the features that would represent a building? So now, these features, they are parts or patterns in an object that would help anyone to identify it. Say, for example, whenever I see an object with flesh, with eye, with nose and mouth, I know that that is a human. So whenever I see object where the legs doesn't touch the floor, then we know that that is not human, something else. Things like that. So these are called features. So say, for example, at a very high level perspective, the features that defines a human would be nose, eyes, mouth. The features that would describe a vehicle would be wheels, license plate, headlights. And the features that would define a building would be doors, windows, and steps. And these features, they don't occur separately. They are a combination of these features which defines a particular item or an object. So these are features. So the reason why we are giving you the high-level context of these features is because in the past, when a computer vision task just begin to, where researchers begin to look into computer vision tasks, what they have been trying to do is to define features. Okay? In order to teach computer or machines to see things, we will need to tell them that, hey, whenever you see a combination of features, you assume that this thing belongs to A, that thing belongs to B. So what are features? Features can include some of the properties, technically, such as corners, edges, regions of interest, points, and ridges. So say, for example, if you were to be able to identify some corners and also the edges, that we would then be able to craft a shape, and we human would know, oh, this is probably a swan or a duck. So these are some of the features that computer would use to identify a particular object. So now, in the past, feature extraction used to be a very manual process. So how manual would this process be? This process can be very, very manual in a way that the computer scientist and a particular domain expert would sit down together and define what features is relevant to a certain object. So now say, for example, this has to be done with collaboration of multiple people, because there are just no pre-built algorithm to find these aspects within an object itself. So it takes a lot of human expertise or labor work to define these features. And the reason why we need to craft this feature is because once we define a feature, we will then be able to identify the corners, edges, shapes, which will then, the computer scientist will then be able to program into the computer system. So this is what it takes for crafting features in the past. So it requires domain expertise to define relevant features. Say, for example, we will need a doctor to define how a cancerous cells would look like in a mammogram. We would need a certified medical doctor to identify the characteristics of pneumonic lung x-rays, things like that. So then what happens is these features will then be hard-coded into computer systems so that the computer system will be able to identify these features in the image. So then what are some of the challenges with this kind of workaround? Is then there are many things that we want computer to be able to see. Say, for example, if we want to enable autonomous driving, driverless car, so then we will have to teach this computer to be able to identify a lot of things that we usually see on the road. So that is just too much if we need multiple domain expertise to define the shape and features of this object, which then can become a problem for the computer scientists to then program all of these features into computer system. So we also talk about a lot of issues such as viewpoint variation. So whenever we try to define these features, once the orientation of thing changes, we will need another set of definition or program that tells that, oh, hey, this item A still belongs to item A. So there are also some challenges such as illumination conditions. On a very poor lighting, so how will this look like? So they will need different programs to tell to tell this system, oh, this is actually still A. Scale variation. So whenever we define the I for a kid or an I for the adult, it could be also different. Deformation. So some animals, they are very naughty and they have just very cute pose and orientation sometimes. Occlusion, background clutter, as well as intra-class variation. So then, all of these variations are the one that makes manual feature extraction extremely not scalable. So they are doable, but we cannot scale if we stick with this traditional approach because they are just label intensive, and it is also very hard to choose the right features and to write very accurate detection code. And all in all, this method is feasible, but they are not scalable. Okay? So then, another group of researchers begin to look into what kind of algorithm, how can we then automate this task using some algorithm-based feature detection method. So then we have a few algorithms that helps us to detect corners, such as Harris corner detection, and also Shine-Thomasy corner detector. So both of these detectors, they are using Gaussian window function to detect corners. So one which is modified according to another to achieve a better corner detection techniques. So such as this image. So then we also know that, then we are able to automate the identification of corners. But does corner tell us what an item exactly is? Well, no. So then, this algorithm has also emerged as we need more and more feasibility. So there are some algorithms such as SIFT, SURF, and also FAST. So all of these algorithms are trying to address a problem which this detection method does not address, which is this scale invariant feature transformation is trying to automate the way we identify a certain corners in a different orientation. This SIF is then able to say, okay, if I see a stop sign with a hexagon shape, and once it is orientated into another orientation, it can still be detected as the same object. So then, SURF and FAST are the improvisation of SIFT in terms of its performance and efficiency. So these are some of the very traditional algorithm-based feature extraction, which helps to automate the task of identifying the corners of a particular object in image. So now these are all traditional corner detection methods. And one of the challenge with this kind of algorithm is that they are very sensitive to noise and they may not provide a lot of description about a certain object in an image. So now the reason why they are sensitive to noise and therefore they may misdetect certain parts of an image, a noisy image, as the corners. So this is what we meant by sensitive to noise. And they are only giving us information about the corners of a particular object, but they do not tell too much about the rest of the object. So this is how have we come so far in terms of corner detection using algorithms. So then, because of all these challenges and also limitation, people have then, as we have more and more computing powers, people are looking into into other techniques called the convolution neural network. Yeah. So now, at a very high level, this convolutional neural network is a type of neural network. So when we talk about this neural network, as you have done from other courses, we know that there are many types of neural network. Some of them are called fully connected neural network, and this is just one of them, convolutional neural network. There are also other types of neural networks such as recurrent neural network, so far and so forth. But the one that is suitable or mostly used for image feature extraction is the one that is called convolution neural network. So we are trying to say that this traditional feature extractor, the corner detectors, can be replaced by convolution neural network because they have a certain ability to extract these complex features and also be able to express the image in more detail. So what we are trying to say is that this convolution neural network, they are so powerful that they are able to learn a specific task or feature more efficiently than those corner detectors. So for example, they are then able to detect low-level features such as edges, dark spots, which then be able to help them to define the mid-level features, which are things like eyes, ears, and nose. So then as we pass on this convolution neural network from one layer to another layer, we can then reconstruct the high-level feature that would define a particular object, such as facial structure. So what we are trying to say here is that this convolution neural network, they can learn a hierarchy of features that is directly from our image data without much of the intervention from human. So yes, we are also saving the trouble of hand engineering these features with the help of convolutional neural network. So then, we talk a lot about this convolution neural network. We know that it is powerful. It can replace hand-engineered features. It can also replace the traditional corner detectors. So then, what are they exactly about? So they are a very specialized type of neural network that is designed for visual data. So whenever we talk about visual data, this would include images and also videos. So sooner or later, researchers in other fields such as NLP and text classification are also looking into using this CNN architecture to do feature extraction from text. So how does it learn? How does this convolution neural network learn? Is ultimately they follow the same general principle of forward and backward propagation. So this is a certain mechanism which helps this particular architecture to learn the features from the image that we have given to this neural network. So now, when we look at this image here, the front part, which is brown in color, are the layers which are relevant to what a CNN would look like. So they are stacking from one layer to another layer. They make up of convolution and pooling layers. They are producing feature maps. So on the right-hand side of this image, where you see blue color dots here, that is another type of neural network called fully connected neural network. So that is the artificial neural network that we have probably come across. So this type of neural network is the one that is also commonly used in other machine learning tasks. So they are fully connected from one neuron to another neurons, which is why they are called the fully connected layer. So taken together, when we put the CNN and the fully connected neural network together in a structure, we can define this as some of the image classification architecture. So in this week lab, we will be building our own architecture to classify certain image. And in next week's lecture, we will be talking about some of the famous architecture which we can also use for our image classification task. So this is a high-level understanding of what a CNN is, and what is the difference between the CNN and the fully connected neural network, the one that we usually know. So now, in the next few slides, what we want to talk about is how this CNN is being different from the fully connected neural network, because this CNN is a very specific and special type of neural network which is designed for computer vision tasks. So on the left, we have all the nodes which are relevant to CNN, And on the right, we have everything that is relevant to fully connected neural networks. So here on this slide, what we are trying to say is a typical convolution neural network, they consist of multiple layers to layers. So the layers that are relevant to this convolution neural network are called convolution, as well as the pooling layers. So we have the convolution layers that extracts features, the spatial features from a particular image, which then we have the pooling layer to further reduce the dimensionality of this feature to make things more efficient. Okay, we are saving space using pooling layer. So at the end of a convolution neural network, that is usually followed by a flattened layer. So this is a way of formulating this CNN, because as much as we are contented with the features which we have been trying to extract layer by layer from our images, we then want this neural network to help us with further tasks, like, for example, classification, detection, so far and so forth. So then once we are good with the extracted features, we will now treat these features as the normal features which we see in structured data, which then we will flatten it and channel all these features into a fully connected neural network for classification task. So this fully connected neural network is a type of neural network where all the neurons are connected from layer to layer. So this makes them very generic. They are not efficient for some tasks like feature extraction, but they are very efficient and useful for other tasks like classification or regression. So that's the first difference between CNN and also the fully connected neural network. So what else are different between CNN and also the fully connected neural network? So the reason that allows this CNN to be able to extract features from image is that we know that image are a 2D array of pixels value. And we know that the values from a particular dot point to another point is related to another to define a particular feature. Say, for example, this piece or this part can refer to an eye. So now, this convolution network is the one that is able to extract some of the information from this patch without losing the spatial information. What is spatial information? That means the orientation of the object in a particular patch, in a particular area. Whereas the fully connected neural network, every neuron, if we were to use this fully connected neural network, what happens is we will have to deconstruct all of this point that refers to an eye into a 1D array. So this makes the item or the feature loses its spatial information. So an eye is now not an eye anymore. So that is the difference between CNN and fully connected neural network. So on top of what we have just discussed, the CNN, this characteristic of CNN is often termed as they have sparse connection. That means they are not fully connected, they are sparse, and they are extracting the values from corners. Okay, so they are only connected to a small region of a particular layer. So from one layer to another layer, they are not fully connected, but they are only connected to a certain part from the previous layer. That helps this convolution neural network architecture to preserve the spatial invariance in a particular image. Yeah, so spatial information. So then, this fully connected neural network, as you have seen from the previous slide, they are interconnected. So one single neuron over in one layer is fully connected to every single neuron of the next layer. So then it allows this architecture or this kind of neural network to capture very complex combination. But if we were to apply it on images, this will make the image lose its spatial information. However, this kind of neural network architecture, they are suitable to be used for other tasks like learning the pattern that would define a certain item or class. So that is the difference between CNN and fully connected neural network. So now we want to talk about how does this convolution neural network able to carry out a task to extract features. So now how it works here is that it takes two elements for this convolution neural network to work. So first of all, we have, say for example, our image, which is big, and we need to have a filter. So say for example, we have a filter size of 4 by 4. That would mean we have 16 different weights. So then we are applying this same filter to patches over this entire image. Say for example, we want to run this filter through every single pixel of this image to extract a certain features. So now we are using this set of weights which are pre-programmed in these filters to extract the local feature from a particular image by sliding this filter across the entire image. So at the same time, we are also able to use multiple filters to extract different features. And all of these features will share a spatially similar parameters in each of these filters. So let's demonstrate this using some example. So say for example, we know that an image is represented in a matrix of pixel values. So in this case, we have 2x, an image of 2x. And one is straight, another one is slightly slanted, probably italic. So now how do we tell this computer to say that, oh, this x is equivalent to this x. They are the same alphabet. So now what happens is that a convolution process is trying to learn the features of x. Say for example, when it sees these two images as x, as predefined as x, it is trying to learn the similarity between the two images. So then the similarity of this feature will then become the features of x. Say for example, an x would have a crossover. So it would usually have a patch that consists of black, white, black, white, black, white in this orientation. And then it will also have a part which is slanted that defines how an x is being written. So the slanted part of the line of an x will consist of two directions, one in this direction and one of another direction. So say for example, these are the features of x. So during a training process of the convolution neural network, this neural network is trying to learn the weights of these filters that define the feature of x as soon as we pass on these two images into the training process. So then what happens is they are constructing these filters as the weights of a particular model. And what happens is we can then use these weights of filters to slide it through a new images that this model have not seen before. Say for example, we have been able to detect 3 kinds of features that would define an alphabet X. So then we have 3 kinds of filters. What we need to do next to for this computer to tell whether another object that it has seen is an X or not is then it will apply these filters which it has learned over new images that it has never seen before. It will try to detect the certain part which is defined by these filters. The similarity between the small patches of item relevant to these filters, and then be able to tell whether, oh, this item is more likely to be, how likely is this item going to be an object X. Okay, so this is how we will then apply the filters, which is learned from a training process. So then, how do we then mathematically compute the similarity, or how does this sliding operation works? So this is called the convolution operation. So during a convolution operation, what it does here is we are taking the element-wise multiply. Say, for example, we slide the first filter that defines the hand of an X over the entire image. So now we are taking the element-wise multiply. So say now, for example, this filter consists of two values, black and white. So all the white which contains the information of a particular feature will be coded as 1, and those which are not a feature will be coded as -1. So as we slide this filter over this entire image, what we are trying to do is taking the element-wise multiply. Say, for example, as we slide this filter through this patch, what we are trying to do is taking the 1 of the filter, multiply by the 1 in the original image, and then the next pixel -1 times multiply by the pixel in the original image, and then we take this one and multiply by the original number in the image. So we are taking the values in the filters times the value in the image, which will then give us this results. So then, what are we doing with the multiply product is then we will add all the outputs to have one value. So now, how does this value fall into place is something that we want to talk about in the next step. So as of now, we just want to know how these filters and image works through a element-wise multiplication and a summation of this element-wise multiplication product. Okay, so what we just talked about so far is the image feature extraction techniques. So we started off with handcrafted features of how a particular domain expertise would define and how a computer scientist would then program these features into set of numbers. Then we talk about this algorithm-based detection, which enable us to automatically detect corners from image. Then we ended the session by talking about how can we use CNN to automate feature extraction process. So, any questions so far? So no, let's see if you understand the concept. So traditional image feature extraction is usually characterized by yes, we don't automate, we don't use the entire image directly, and it is a manual definition. So what is most important for a computer scientist in manual feature extraction? It is the domain knowledge, because the ability to define the right feature will determine how well a feature detector would be. Compared to CNN, traditional feature extraction methods are, well, we know that they are feasible, but there is one particular aspects of traditional feature extraction which is slightly better than CNN. It requires less computation power for that because they are very simple. So it's C. Compared to traditional ones, how does a CNN approach image feature extraction? how does this CNN work? So yes, it learns feature automatically from our training data through forward and back propagation. Benefits of using CNN. The one that is highly sensitive to noise and variations are the algorithm-based corner detectors. The one that requires least computational power would be manual definition. And yes, they can learn hierarchical features. Okay, so then in the next part, what we want to go over is how the CNN operates, how this CNN would operate. As we mentioned just now, we have a filter, we have an image, we have a filter, and how do we slide this filter over a particular image, and what happens after sliding this filter through the entire image. So the first component of this CNN is called kernels, or a filter. So this filter, as we slide the filter over the entire image, it will then produce us an activation map. So we'll see how this works. So earlier what we have seen is that whenever we slide a filter through an image, we are trying to multiply every single box of them and taking the sum. So what happens to a sum is it will be put as the output of the next layer. So the next layer here refers to a feature map. Okay. So what we are trying to say is, okay, so now we slide this filter over the corner of the image. So then what happens is we will slide this filter by 1 pixel and try to extract the features of this spatial dimension. So from these spatial dimensions, what we see is a number of 3. So this will become the next value, or the value of next pixel in a particular feature map. So then as we slide this filter through another pixel, we are then producing another values which make up the next value of your feature map. So then as soon as we finish passing this filter through the entire image horizontally, we will then move this filter down vertically by 1 pixel. So now what happens is that we will slide this filter through this row to capture the spatial information within these patches. Okay, so now this process will repeat through the entire image to produce the feature map that extracts certain information from this patch. Okay, so that is what happens. So then, what happens to what's on top of this convolution operation is that we are trying to apply a non-linearity after every convolution operation. So what this means is we will be using an activation function which is called ReLU. So now this ReLU is a pixel by pixel operation that will eventually replace all the negative values with 0. Say for example, as soon as we produce a feature map from a particular process, the feature map can cover a wide range. Say for example, black which are negative and white which are positive value. So then how do we rectify this feature map is then we will apply a non-linearity activation function to then rectify the feature map to say that, hey, we only retain the non-negative values in a particular feature map that is to be used in or to be channeled to the next layer of convolution neural network. So that is non-linear, introducing non-linearity into the process of feature extraction. So again, this is just a recap on what this kernel is about. So this kernel of filters is the weights within these kernels of filters, the numbers within the filters, are the exact weights or things that we are trying to learn in the process of training a particular model. Okay, so in the training process, what we are trying to do is to find out the weights of these filters. So then, okay, so then how do we put all of this together in terms of kernels of filters? So they are designed to extract specific features. Say, for example, we have a huge image where we are trying to use this CNN to extract a particular features. Then these features will then be outputted as a feature map that is going into the next level or next layer of convolution neural network. So this can be passed on to more and more convolution layer to learn its mid and high level features of particular objects in the input image. So then, by stacking multiple layers of this CNN and max pooling together, we are then able to detect the edges, curves, colors, parts of object, and a complete object. So this is how the convolution layer, operation is. So then, when we talk about this sliding operation, there is a very specific term that is assigned to it. So the term is called stride. So what is stride? Stride defines the kernel step. Say, for example, we mentioned about sliding this one pixel across. So this means a stride length of 1 pixel. So we can also increase the stride length to 2 pixels. So in this case, we will retain less feature or less information from this piece, but we minimize the space that is required. Yeah. So and then we extract lesser features from that. So this is stride. So the technical term for sliding filter over a particular image is called slide. And usually 1 pixel and 2 pixel stride is very common. So well, higher stride length is less common, but it is possible. Yeah. So then when we looked at the convolution operation, one of the very obvious difference between the feature map and the original image is that the feature map now strings with each layer that it goes. So then, are we able to maintain the dimension of this feature map? Because sometimes we want to stack a lot of layers of them, and how do we then maintain a particular dimension of the feature map in the early stage or the early layers? So then we want to introduce a concept called padding. So padding is a concept where we will now add some generic pixels around the original image. So then, as we slide this feature map through the generic layer, it is able to retain the shape of the feature map, the dimension of the feature map as per its original image size. So that is padding. We are adding some generic pixels which are coded as 0 around the original image so that we retain the size of feature map to its original image size. So then we are extracting multiple features, which then it will take up a lot of space and it makes the process less efficient. So how can we maintain high efficiency while maintaining the features information that is captured within the feature maps? So then there is an operation which is called pooling. So now say, for example, pooling, max pooling is one of the common technique in pooling. So this max pooling is a technique that addresses a problem called how can we downsample at the same time still maintain the spatial invariance. So now what are we trying to do here is that we will then slide additional pooling filters through the feature map. So as we slide these filters through the feature map, what we are trying to do is to extract the biggest or the maximum value of that particular patch. Say, for example, even if we lose the information of the smaller values, we still maintain the most obvious feature within that particular patch. So then we are then able to reduce the size of the original feature map while still maintaining the information within the patch to a smaller size. So this is pooling. Yeah. So then, as we put this convolution pooling layer together into a particular architecture, this will allow this architecture to then learn or extract features from image. So the three operations that usually work together is the first one that we went over, convolution, nonlinearity, and finally pooling to downsample the operation. Yeah. So there are still a small part after this session, but I think I will just end the session here, and we shall continue the rest next week. Yeah, we shall dismiss the class. Have any question? So those who are having